Okay, we have to start the next chapter, cubes and then cube roots. Let's start with the introduction. So this is a story about one of India's great mathematical genius S. Ramanujan. Once another famous mathematician, Professor G.H. Hardy, came to visit him in a taxi whose number was 1729. While taking to Ramanujan, Hardy described this number a dull number. Ramanujan quickly pointed out that 1729 was indeed interesting. He said it is the smallest number that can be expressed as sum of two cubes in two different ways. For example, if I break 1729, 1728 plus 1, then 1728 is the exactly cube of 12 and the 1 is exactly cube of 1. And then we can make exactly cube of two different numbers in a two different ways. 1729 has since been known as the Hardy and the Ramanujan number. Even though this feature of 1729 was known more than 30 years before Ramanujan. How did Ramanujan know this? Well, he loved numbers. All through his life, his experiment with the numbers, he probably found a number that would express as the sum of the two squares and the sum of the two cubes also. There are many interesting patterns of the cube. Let us learn about the cubes and the cube roots. For example, this is a cube and how we can do the cubes and the cube roots. Perfect cubes or cube numbers. For example, if the number that is present like a thrice time, you can make a cube of that number. Okay, just like this. You can make a cube of that number. For example, 1 by 1 and 1. You can make a cube of a 1. If there is, but the cube should be of a same number. If I can say that 2 into, you cannot say 2 into 3 into 4 are the cube roots because these are the different numbers. We cannot say that. But the same number, cube root is only for the same number. Okay, like 2 into 2 into 2, 3 into 3, 10 into 10, and any number should be same. Got it?
Yes.
Okay. So this is how you can work and you can solve any number. Look at the table. 1, 4 cube 64, 5 cube is 125. You have to multiply the number like thrice time with each other. 5 multiplied by 5 multiplied by 5, 125. Now the 6, 3 times 6 is 216. Okay, and so on. You can complete this table. Got it?
Okay. Yes.
Now the next is some interesting patterns. So this is the interesting pattern. 1 plus 1, 1 cube. Even you can get a cube by adding two different numbers. For example, 8 is the cube of 2. When you add 5 into 3, you get the 8. You can add any number to get the cube root. 7 plus 9 plus 11 give 27. And the pattern is like this. One step by step increasing by the even numbers, by the odd numbers. Understood?
Yes.
Now the next thing is cubes and their prime factors. Prime factorization of its cube. For example, you have to get the prime factorization by using the LCM. You have to use only prime number. Prime numbers are the number that is present in one and in their own table. Got it?
Yes, ma'am.
So, and this you have to do the prime factorization like that. There on the page number 112, they did the prime factorization of 216. Same thing. They use only the number that is present in their own table and the ones table. If the numbers comes like a thrice time, then you can make a cube's root. Cube. Okay? Cube of that number. Means index notation. Index notation. Got it?
Yes.
Let's do the 7.1 exercise. Here's exercise 7.1 in which we have to solve each number according to their perfect cubes. If we find any number, we have to do the prime factorization. If we find the exactly cube of the same number, then that will the given number is the perfect cube. For example, first is 216. 216 is the exactly cube of 2 and 3. if any number like present in a twice time and if the present in not in even manner, that is not a perfect cube. Okay, I did the first part. Now I will do the fifth part. So the fifth part is 46,656.
Okay.
46,656. So I think it will start from the 2, because 2 2s are 4, 2 3s are 6, 2 3s are 6, 2 2s are 4, 2 8s are 16. Clear? Now the next one.
Yes.
Again, 2 1s are 2, 2 1s are 2, and then 2 6 are 12, 2 6 are 12, 2 4s are 8. Now 11,664 again with the 2, 2 5s are 10, 2 8s are 16, 2 3s are 6, 2 2s are 4. 5,832 again with the 2, 2 1s are 2, 2 9s are 18, 2 1s are 2, 2 6s are 12, 2 2s are 4. 2,916. Now understood here still?
Um,
Or facing any difficulty?
no, ma'am.
2,916 again with the 2. 2 1s are 2, 2 4s are 8, 2 5s are 10, 2 8s are 16. Now 14,058 again with the 2. I will continue here. Again with the 2. Then 2 7s are 14, 2 2s are 4, 2 9s are 18. Now the 729 is will by the 3. How? Here 3 2s are 6, 3 4s are 12, 3 3s are 9. Now 243 again with the 3. 3 8s are 24, 3 1s are, 3 9s are, 3 3s are.
27.
Then how many 3s we have?
We have 3 threes, 4 threes.
No. Wait, 81. 3 3s are 81. Then no 3 9s are no. The 3 9s are. I did it
Three.
wrong. Wait. Now the 81 is. Now the 81 left. Na 81 is divided with the 3 2s are. 3 2s are. I cannot use a prime number. Any other number we have to use a prime number. Then 3 2s are.
3 to 6.
And 3 7s are 21. 3 2s are. Then 3 9s are 27. 3 9s are is not a 81. Three 2s are 6 and then 27. So the 27 here, 3 3s are 9 and the 3 1s are 3. 1 2 3 4 5 6. 1 2 3 4 5 6. I think this is a perfect cube. How? Look here. (46) into 656 makes 1 2 3 4 5 6. 1 2 3 4 5. Do you think it is making a perfect cube root?
3 1 6. Yeah, ma'am.
Yes. 2 cube, 2 cube, 3 into 3. This is how you can find the cube root of any number. Any question?
No, ma'am.
So the question number 2 is find the smallest number by which each of the following number must be multiplied to obtain a perfect cube. We have to find the smallest number. For example, for the 243, it seems that in this number we will get only one cube root set. Okay, let me do the question number 2. First part is 243. It will give only one set, that will be the smallest number. So 243 will be with the, I guess, 3. Yes, 3 6 are
3 6 3 1 6 6 1 6 6 1 6 3 are 18.
3 6 are 18. Then 3 8s are 24. 3 1s
Yes,
are
ma'am.
3. Then 81 divided by 3. 3 2s are 6. 3 7s are, then 3 9s are, 3 3s are, 3 1s are. I will write the factors, multiples. How many 3's we have?
We have 3 3's, but we have only 2 more left. So 5
Yes.
are there.
So only the number. So the 3 are left which are not a triplet. To make a 243 a cube, one more 3 is required. In that case, 243 multiplied by 3 and all the digit 729 is a perfect cube. So hence the smallest natural number by which 243 should be multiplied to make it a perfect cube is a 3. So for example, there is only one more 3 is needed to make a perfect cube. Okay, so the smallest number, for example, if I add 3 here, that will make an exact cube. Okay, that will give me a 243. Okay,
Okay.
so the smallest number is, you just have to give, when you have to find the number that will be the smallest number
Okay.
is 3. You just have to write like this. Okay,
Okay.
can you do the rest of the questions?
Okay, ma'am.
If you want to, if you understood everything, then
Okay, yeah.
if you find any prime factorization with 2 3 4, if the one number is missing, that will be the exactly for the 256. All 256 is solved by the 2, and we find a perfect cube root, but we didn't have a last 2, that will be the 2. Okay,
Okay.
so the question number 3 says, find the smallest number by which each of the following number must be divided to obtain a perfect cube. We again have to find the smallest number which is divided, not the multiple, which is divided to obtain the perfect cube. For example, for the 81, if I get the perfect cube, if we divide 81 with that number, it will become a perfect cube. Okay, we just have to find the perfect cube. So if I underline the values that are underlined, okay,
Okay.
we have to find that perfect cube. Okay,
Okay.
for example, let's do this 81 part. Question number 3, first part, 81. 3 2s are, 3 2s are, 3 7s are, 3 9s are, 3 3s are, and 3 1s are. So set is here 3 into 3 into 3 into 3. Then these are all. So only 3 is left. If this 381 is divided by 3, we will get the exactly same cube root of this number. So only 3 is left, which is not in a triplet. If we divide 81 by 3, that it will become a perfect cube. Okay, if I just move this 3 here, it will give an exact perfect cube. So you can write like this, 81 by 3 will gives you 3 into 3 into 3. Understood?
Yes.
is a perfect cube. So the smallest number by which 81 should be divided to make it a perfect cube is 3. Again, 3 is the smallest number for the division. Okay,
Okay.
understood?
Yes, ma'am.
Can I move to the question number 4?
Yes, ma'am.
Parishikit makes a cuboid of a plus the sign of side 5, 2 and 5. How many such cuboids will he need to form a cube? He just pick a little bit cuboids with the same side, and then what one is opposite 2 centimeter. How many cube he need more to make a cuboid? Some cuboid size 5 into 2 and a 5 are given. Okay. And then when these cuboids are arranged to form a cube, the side of this cube is formed will be the common multiple 5 into 2 and 5. So the LCM of 5 and the 5 is 10. Both have the least common multiple as a 10. So we have to find the arrangement, and we have to put the cube with its length along with the width along with the height. Then we will find this. So I guess we have to multiply all of these. 2 multiplied by 5 multiplied by 2. 2 2s are 4. 4 into 5. So with the help of 20 cuboids, such measures a cube is formed. Okay. So that this question will be done like this. So the small cubes with the centimeter 1 cube, the length, the height and the width is like this.
Okay.
Into 2 into 2. The length, the breadth and the height. When we multiplied each of them, all of them, I will get 20 centimeter. So if I have a cuboids with all of these sides, length and breadth, I multiplied each cuboid length, breadth and height, I will get the one answer. That will give me the exactly how many cuboids I need to build a cube. I need 20. Okay?
Okay.
Understood? We have done only the cubes. We have make a scientific notation, index notation with the cube. Now the cube root is the different thing in which we have to put a cube under a root. Okay? A side of the root. When we put a number, we have to find the prime factorization. When we get the exactly cube, that is the exactly number. Okay? Any questions?
Yes.
Any question?
No, ma'am.
So yes, let's finish the exercise 7.2, the last exercise of this chapter, and our syllabus as well. Okay?
Okay, ma'am.
Exercise 7.2.
2.
So in the exercise 7.2, the first question is find the cube root each of the following numbers by the prime factorization method. We have to follow the same previous rule in the 7.1, but we have to put the root. For example, this is the first part, 64. I have to put the cube here. I will do the prime factorization. Okay? And the prime factorization of 64 is we have to multiply 2 like a thrice time. Okay? So 2 into 2 into 2 into 2 into and then into 2 again. Okay? So we just have to make a cube root here. Cube root here. This and this. 2 into cube. 2 into cube. Do you know this? We can separate them. We can neglect this. For example, I am making a common 2 cube. And this cube is cancelled with this cube. This cube and this cube root both will be cancelled out with each other. How? Same thing we did in the square root. Cube root is cancelled and the left thing is 2 into 2.
Yes.
What is the answer? 4. So we can say that the perfect cube root of 64 is 4. Understood? If we
Yes.
didn't get exactly cube root, that is question will not be solved further. Okay?
Okay, ma'am.
So the first question, all the parts, you just have to do like this. Okay?
Yes, ma'am.
Okay, can we use the true and false?
Yeah.
Okay. So the state true or false. Cube of any odd number is even.
Mm, yeah.
You know, cube
Odd
of
number.
any odd number is not an even.
It's always odd.
When we find out the cube of an odd number, we will find an odd number as a result because the unit place digit of an odd number is odd and we are multiplying 3 odd numbers. Product will be again an odd number, not an even number.
Yeah.
First one is
Okay. Odd number.
false.
False.
A perfect cube does not end with 2 zeros. Perfect cube will end with certain number of zeros that are always perfect multiple of 3. True.
So it's true.
Third one. There is no, if square of a number ends with 5, then it is cube ends with 25.
No.
Third one. It is not always necessary that if the square of a number ends with 5, then its cube will end with 25. No, this is false. Fourth one. There is no perfect cube which ends with 8.
False.
There are many cubes which will end with 8. The cubes of all the number having their unit place too. And for example, cube of 12 is 1728. So that is false.
False.
Fifth one. The cube of a 2-digit number may be a 3-digit number. False.
The cube of a
Smallest
single digit
two.
number.
We are doing the fifth one, na?
Yeah.
The smallest 2-digit natural number is 10 and the cube of 10 is 1000, which has the 4 digits in it. So it is false. Sixth one. The cube of 2-digit number may have a 7 or more. No, that is false. The largest 2-digit natural number is 99 and the cube of 99 is maybe the any which has a 6 digit in it, and therefore cube of any 2-digit number cannot have 7 or more digit number. Last one. The cube of a single digit number may be a single digit number. True. Cube of 1 and 2 are 1 and 8. True. Okay. So the question number 3. You are told that 1331 is a perfect cube. Can you guess which factorization is its cube root? Similarly, guess the cube root of this and this. We will do this question in the next class. Okay.
Okay, ma'am.
We have finished the exercise 7.1, 7.2, and in this exercise first you have to learn the cube roots with the help of prime factorization. When you find the exactly cube root of the same number, that will be the exactly cube root of the given number. If we didn't, that is not. In the 7.2 we learn how to cancel the cube root. Okay. I hope you understand each and everything of this chapter.